Hello everyone. In this video we are going to talk about ODE events which are going to interfere in integration of an ODE solver. For instance, let's say you want to look at the motion of a projectile in the air, let's say with or with no air drag, and whenever it hits the ground, now you have to stop the integration, because if you don't, the y is going to go negative. So you have to stop the integration, change the initial condition, in this case basically changing the y velocity to negative e times the y, so that comes from the impact and the coefficient of restitution, and keep doing that. So how would you do that if you want to do it just with ODE solver and not with Simulink or anything, right? Because in Simulink you have the stop block that you can stop the simulation if some condition happens, okay? But here, how would you do it in ODE or any other condition, right? When something happens for one of the variables in your system, you want some action to be taken, okay? So you have to first detect when that variable has passed some limits or reached some limits or something happened. You want to detect that event and then take an action. So the event that you can have in MATLAB, typically they happen when a variable, an expression, is equal to 0. When something crosses 0, when a 0 crossing happens, an event is basically detected and a flag is raised, okay? So in this case, when the y of the projectile goes from positive numbers, which are right above the ground, to the negative numbers, which is below the ground, so when y crosses 0, that's when you can detect that the projectile has hit the ground, okay? So that's what we need. We just need to look at y variable and see when it hits the 0 value. And let me show you how it is done if you want to do it. So here, as you can see, I'm doing a simulation, and in this simulation, this is what I'm doing. I set up the initial condition for the projectile, so launching from origin with velocity of 10 meters per second, angle 45 degrees, g is 9.81, the coefficient of restitution is 0.8, and the threshold for when to stop all those bouncing is when the Vy is no bigger than 1 meters per second. Okay, initially your Vy is quite a bit bigger than 1 meters per second. You can see that it is about 7 meters per second in the beginning. So it is going to do a bunch of bounces. Each time it is reduced to 80% of what it was before. And because here we don't have any drag, and then you keep going until it falls below 1, and then you stop, okay? And if you want, you can make this threshold as small as you want, okay? So you can make it as close as possible to 0. Now here, each time for each one of the motions between the ground and the next bouncing, I use a time span of 10 seconds. You need to make sure this final time is big enough to allow for the entire integration to be done from the launch position to the next point that it hits the ground. If this initial velocity is large, or this angle is large, or both, then you might need a bigger time here that makes sure that it is enough for one launch of the projectile from the ground to the next point. These t total and y total are basically the placeholders for the time and for the state space variables. These impact times are all of the times that the projectile is going to hit the ground. I'm going to also collect them. And the last time is 0. I'll tell you what that one is. So here you see I'm using a while loop, and I say as long as the initial condition number 4, which here you can clearly see that's Vy or V0y, as long as this initial condition number 4 is bigger than the threshold, keep doing it. What would you do? The first thing is that the option here that you need to add the ODE event is determined in option of ODE, or ODE45 in this case, and I do it with the command ODE set. So I say ODE set, and I want you to detect some events. What event? The event that is determined by this function, ground event. This function ground event will take time, will take the state vector and some parameters, and it will basically give you some outputs, okay, as we're going to see. So this one will give us, when it hits the ground, it detects the ground hitting. And then with that event, I'm gonna pass that option with that event. I'm gonna pass it to ODE45. In the ODE45, I have a function which basically determines or writes down the governing equations of the projectile, okay? Time span, some initial conditions, and it gives you some output. So let's talk about these. So what is this ground event function doing? If we go down and look at it, it takes time. In this case, we don't need time. It doesn't depend on the input time. It only looks at the, basically, if you look, it only looks at the y number 2. Now here, this capital Y is not the same as the y of the projectile. The y of the projectile is only the second component of this capital Y. Okay, so this capital Y in this case is a state vector which has x and then y and then x dot and then what? Y dot. It's a 4x1, and you can see that here. Okay, so this function here takes all of those values, the parameters that you need, and these parameters is, in this case, is a structure with 2 values, g and e. And as I said, we don't need time, so we can use this tilde instead. And it returns 3 values for you. Value is terminal and direction. Value is the thing that you are monitoring, so it does cross 0. In this case, you see the value is y of 2. So here you say, hey, look at y of 2, which is the y value. As soon as it crosses the 0, go ahead and raise the flag. But how should it cross the 0? Because if you look, when I have some value, right, when some curve passes 0, crosses 0, it can do it in 2 different ways. It can go from positive numbers to negative, or it can go from negative to positive, right? So here, by this direction, you are telling it which way it should go. By -1 means going from positive to negative, or it's decreasing and hitting 0. If you say +1, means the number was negative, now it is going to go positive and crosses 0. And if you say 0 for direction, means both ways. It doesn't matter, it goes from positive to negative or negative to positive, you raise the flag. Okay, so this direction thing will basically check for in which direction it crossed the 0. In this case, since we are going above the ground, hit the ground, and we don't want it to go below the ground, so we are going from positive y's to negative y's, so we use direction of -1. Then you have this variable is terminal. If you say this one is 1, means what? Means stop the integration. If you say this is 0, means don't stop the integration, keep going. But here we want to stop the integration so we can change the initial condition, the initial Vy, right? We want to change that due to impact. So here you say is terminal 1 or true. Yes, do stop the integration. So I can do what? If value is 0, which means if your y is 0, if you're crossing the y, which you should, then what? Y of 4, which is Vy, change it to what? To whatever it was, but times -e. Here is applying the coefficient of restitution to update the Vy. You see? So it gives you what? It gives you, it updates the y value that you gave it. So the integration in the ODE solver uses this new y, and it also returns the value terminal is terminal and direction. Okay, so this is how you write this function. Good? Yep. So, and here you can see that I use that function to detect events, and I pass it to my ODE solver, ODE45 in this case. Also, I have the projectile ODE, which are the governing equations for ODE, and these are the governing equations. It's very simple. In this case, the derivative of x, or y of 1, is y of 3, So it's v of x. The derivative of y is what? Is vy, or y of 4, which you can see here. The derivative of vx is ax, and ax for a projectile with no air drag is 0. And the derivative of vy is ay, and ay is simply negative g. Okay, and that's what you can see here. So this function will only give us the right-hand side of the first-order derivatives, and that's what we want for OD45, first-order derivatives. Okay, and if you have air drag, the expressions for ax and ay will be a little bit more complicated, but you can easily add that. It's not a big deal. So that is my ODE function that you have, and the time span. And here for the time span, I use a time vector instead of just 0 to 10. I give it a resolution here of 0.1, because if you don't, the number of time points that it uses between one hit to the ground and the next is going to be very limited. And the animation that you'll see is those curves, those parabolas, are going to be kind of broken and jagged instead of smooth. So here I use a small resolution, and if it's not enough, you can even make this number, this time step, smaller. Okay, so that was for the event and the governing ODEs. Now, when you call the governing ODE and ask for solution, in the past, if you watch my videos, I typically only get two things out of it. One is the time points that it used, and then what? The state vector y. Okay, but here, when you define events, you can ideally get 3 extra outputs out of the ODE solver. Not only you can get the time points and the state vectors, you can get 3 extra inputs. What are outputs? What are they? TE, the time of the event. It shows all of the times that the event occurred. So basically, this is all of the times that the projectile hit the ground. Okay, all of those time points. YE involves the solution. It contains the solution, which is this state vector, anytime the event happened. So basically, it gives you all the values of x, y, vx, and vy at the time of impact. Okay, that is the YE. And of course, you might have IE. What is that? These are the indices of the vector returned by the event function. Okay, which indices of this y or t is when the event happened. And most of the time you don't care about that, you just care about this t and y. And here I'm going to use these t's to show on the animation graph the times that the projectile hit the ground. I'm not interested in ye, but I get te, and for the other two I use tilde because I don't want them. Okay, and you can see that te here that I get, I'm gonna store it to my impact times, because later I use those impact times in a for loop to do what? To show right where next to the place that the projectile hits the ground, I show what? I show a text, and that text shows what? The impact time right next to my projectile hitting the ground. Okay, so this for loop is just to show the times of the impact next to the plot. This next for loop is for the animation, of course. Okay, so now you can see the whole program, and then this t total, as you can see, it stores what for me? It stores basically all of the times that I had from the solution. You keep storing them, so your final t total will have all of the time points, and this y total will have all of the state vector solutions. As you can see here, you're appending or doing concatenation. Okay, so you have t total and y total, and then what you need from the y total are only the first and the second column of it, which are what? X values and y values, because we only need to plot x versus y for the projectile. Okay, so I think you can see how this problem is done, and here we go and run it for you. Look, did you see? So these are all of those times of the impact that, as I said, are shown right next to where it is hitting the ground. And these are all of the projectiles the path of them, and you can see that although I use 0.1 for the time step, still this is not really smooth. So you can use smaller values, okay, and it is going to make it smoother. And here I stopped when the Vy0 was 1. If I use a smaller threshold, this one keeps going for a bunch of smaller bumps. Okay, so if that 0.1 is not enough, you can always change it to, I don't know, 0.01. Now, of course, it takes some more time, but it is going to allow what? A smoother curve. And if the animation is too fast, then you can make it a little bit slower by something like this. Okay, so this should do a little bit better. You see, now the projectiles are very smooth and the animations are a little bit slower. And it is also showing all of the impact times, which I got from the event. And you see the event stopped the integration, changed the Vy, and also when I called ODE45, it gave me all of the times of the impact. So you see it is doing this beautiful thing. So this is how you run an ODE event by a function and how you get extra information from the ODE solver. Now, a few things that I need to mention. One is we said that here we need to monitor a variable and make sure that it crosses 0. Now, the root finding or the zero crossing mechanism that this ODE solver ODE event has, it has some limitations. So we need to keep them in mind. One, if a terminal event occurs during the first step of the integration, guess what? It's not going to do anything. It's not going to raise any flag, and it continues integration. So, and what does that mean? Well, look, initially your Y, you're starting at 0. So if that's the case, and this guy is only after what? After Y's of 0, that means right off the bat, without even you starting the integration for the first flight, it should stop, right? It should raise a flag and say, hey, Y is 0, I detected it, stop. No, because that's the first time. So if your first Y value is 0 or non-zero, it doesn't make any difference. Your integration keeps going. After that, if it goes to 0 with a direction of -1, then it is going to raise a flag. 2, if more than one terminal event occurs during the first step, then only the first event registers and the solver continues integration. And finally, zeros are determined by sign crossing between the steps. As I said, going from negative to positive or positive to negative. If you have an even number of crossing, it could be missed. So if you hit the ground and go from positive to positive, but hit at Y of 0, then it's not going to detect that. It should change a sign here. Now, this method of event detection and event handling is for versions of MATLAB that was before 2023B. In 2023B and after that, the structure has changed a little bit. So if you want to handle the same problem here, now your ODE event, you can define something called an ODE event. There is this new function that is only available from 2023B and afterwards. There is this new function, and here for the event function, you define the function. This is like that ground event that I have. And for direction of it here, you define a descending or ascending, okay, or both. So you don't need to say -1 or +1, you just say descending or ascending. And what happens when an event occurs, you can have a separate what? A callback function for it in response to it. And the response to an ODE could be proceed. So this response could be proceed, which means just do whatever you were doing, don't care about it. Stop, which means stop the integration. Or what? It could be callback, which means do whatever the function in the callback is asking you to do. So this callback is more general, right? You can do lots of things in it, okay? So here you can, for response, you say, I want a callback according to which function? According to this function called the bounce response, the callback function. Okay, so with the ODE event, you define everything, and now when you go to ODE 45, you say ODE function is whatever the function for governing ODE's initial value, and then what? You say event definition equals E, equals whatever you defined with ODE event. You see, last time I had to use ODE set and options. You see that here? Let's go. So you define options from ODE set and event, and then you passed it as options to the ODE solver. This time use this new function ODE event. And then you say event definition equals this variable, this handle, and you do that. And again, of course, this time you can also ask for what? For TE and YE and IE as well here, okay? You can still receive all of those variables, but the way that you define event is a little bit different in the new version. Just wanted to tell you that. So here, this is the ODE Z dot. This is the one that I need for governing ODs, which you can see is very simple. And the bounce response, look how the bounce response is. So you pass to it the T and the state variable, and it can give you back the new state variable and a variable called stop. Now here for the stop, I say false, means don't stop integration. Keep going, but what? Make Z number 4, the Vy, to be E times Z number 4, updated, and Z number 2 set it to 0. Okay, and here it is already 0 when the event happens. Okay, but clearly you see that when the event happens, this is the response to that event. Okay, this is what it does. And what is the event? The event is, as we said, that if you look at the bounce event function, this is at T and Z, Z1. Okay, and actually it's wrong. It should be Z number 2 because my Z number 2 is Y, my Z number 1 is X. So here, what is it? You say, well, the function that detects the event is look at Z number 2, which is Y, and make sure what? It crosses 0, which could be in the ascending direction, descending like here, or both, which is the default one. Okay, so here you see instead of writing separate functions for the ODE function and for the event, I use the anonymous functions. And you can do that as well. They don't need to all be functions like this. If they are so simple, like in this case, instead of all of this, in this case, I just wrote what? I just wrote this anonymous function, and it does the job. Or if all you care about is Z number 2, which is the Y variable, right? Instead of this guy here, basically, that's what you did. And handling it is done with this separate function, but you see here, the handling of the event is also done inside the event function, like that. Okay, so these are two different ways that you can handle this problem, and they should give you similar results. But here, I'm going to share this first one with you in case you don't have version 23b, and afterwards, you can still run this one, and you can learn from it by playing with the code. So, thank you so much for your attention, and I'm going to see you in the next video.